The rate of the blood flow is dependent on pressure difference divided by the resistance. Now, what do I mean by this? Right, by seeing it right here as we kind of write it down. Right. Let's think about the flow right here. Flow is dependent on P1 minus P2 divided by resistance. Now the resistance, if you take a look at it, is going to be where resistance is equivalent to 128 times the viscosity times the length of the vessel divided by pi r to the fourth. That's a lot of math. That's a lot of different things. You're going to see in a second, I don't like all those variables, so we're going to cross them out, all right? Or the constants, all right? So what we're going to see is, what is pi r to the fourth power? That is the area of a tube, all right? All right, remember, pi r to the second is what? Well, the area of a circle, right? So here, we're going to see that the resistance is going to be dependent on the size of, right, the opening, which kind of makes sense, right? And we're going to see that, so R, 128, viscosity times length. And again, right, since R is on the bottom here, anything on the bottom gets inverted to the top. Pi r to the fourth. We're going to see this radius to the fourth power, that's to the fourth power, right? So if you increase it just a bit, you're going to increase the flow to the fourth power, right? Now, what about this pressure difference? So again, kind of give you that warning. Here's my blood vessel. In order for blood to move in this direction, I want it to move from the left to the right. It makes sense, all right? This is my pressure at the start, P1. This is a pressure at the end, P2. If I want it to go from left to right, I need more pressure in the beginning, don't I? To force it to move in this direction, right? Now, the greater the pressure at the beginning, the greater the pressure here, the faster I can move it. So this is where we get that pressure 1 minus pressure 2. It's basically the difference in pressure. So flow is dependent on the difference in pressure. If I have more pressure at the very start, P1, then at the end, I move it in this direction. What would happen if I have greater pressure in P2 than P1? Greater pressure at the end than at the beginning. Well, you're going to have it in reverse, right? So the greater the pressure, right, the more you move in that direction. So if I have more pressure in P1, I can move it in this left to right direction. All right, even better yet, what happens if P1 is equal to P2? There's no movement, right? You need pressure difference for blood to move in any one direction. So what we're going to see is flow is dependent on some kind of pressure difference. More importantly, now that we put that actual formula up, I'm going to cross out a whole bunch of stuff. Right? So the first very bottom part, I'm going to cross off the 128 VL, right? Because as we go from one part of the blood vessel to the next, your viscosity isn't going to change. The length of the vessel is going to change, right? It's going to stay the same. What does change, though, is your radius, right? So what happens? In terms of our blood flow, the biggest kind of variable, right, that can cause the biggest change is not pressure in any one direction, right, but this, because it's to the fourth power. Meaning what? If I increase the radius from 1 millimeter to 2 millimeter, what happens? What happens is this. If I go from 1 millimeter, 1 to the fourth power is 1. All right? How about 1, all right, 2 to the fourth power? That's 16. All right? We can have a 16-fold increase by increasing your radius 1 millimeter. which is crazy. That's a huge increase, isn't it? This is why vasodilators work so well, right? It's because by increasing the size, the caliber, just a little bit, I can increase blood flow. And what we're gonna see is the faster blood moves, the less effort it'll take, and they'll decrease your blood pressure as well. Now this is true as well in reverse, right? I can increase flow by going from 1 to 2. I can also decrease it from going 2 to 1, right? This is not just a small decrease, it's a massive decrease. So if I am working out and I want to redirect blood flow to my skeletal muscles, the blood vessels leading to the skeletal muscles increase from 1 millimeter to 2 millimeters in the radius, increasing blood flow 16 times. How about in the GI tract? In reverse, right? In the GI tract, I cause vasoconstriction. In the GI tract, constricting and decreasing the radius from 2 to 1, decreasing the flow 16 times. Now, that's for just if it's 2 to 1. What happens if you increase it or decrease it where your radius is 3? That's 81, all right? You can increase it 81 times, not 81%. Now we're talking about 81 times. That's like 8,100% increase or decrease, just by increasing, decreasing the radius a very little bit. Now, obviously, millimeters are gonna make a big difference, right? So just keep in mind that in general, the biggest thing that can affect blood flow is the radius. Why? It's because it's to the 4th power, right? Because it's not just like a simple 1-to-1 ratio. If you increase the radius like 1 or 2 millimeters, you take it to the 4th power increase. So it makes a huge, huge difference. Also in reverse as well. Right? We call this Poiseuille's law right here. By increasing, decreasing it a little bit, the radius, we can increase, decrease the flow tremendously. Again, right, if you take a look at this, there's a lot of different math here and a lot of, I'm not gonna have this kind of question for us on the exam where I ask you to kind of find the flow. I would ask you to know the relationships, which is if I decrease, right, radius from 3 to 1, what happens to flow, right? And we kind of talked about what happens here already. What happens is if I decrease radius from 3 to 1, I'll see a decrease in flow that's 8,100 times less than what it was before, which is a huge, huge, huge decrease. All right, viscosity, measure of resistance of liquid to flow. As viscosity increases, pressure required to flow increases as well. So viscosity plays a big role in terms of blood pressure, right? The thicker, the heavier the blood, the harder it is to push, the more pressure it requires to push. All right, now, in terms of pressure, right here, last thing I'll talk about is this law right here, Laplace's law. What is Laplace's law and what is all this over here, right? Critical closing pressure is a pressure, the critical closing pressure is a pressure at which a blood vessel collapses and stops, and blood flow stops. So at what pressure do you prevent more flow? Obviously, if I'm doing the blood pressure cuff test, right? Doing the blood pressure test, if my blood pressure is at 120 systolic, at 121 millimeter mercury in the cuff, all blood flow stops. That would be our critical closing pressure. Laplace's law is something that I would have you guys know. Obviously, it's got a lot of red highlights on that one, right? Laplace's law, force acting on a blood vessel is proportional to the diameter of the vessel times the blood pressure. Meaning what? Meaning that the largest arteries will find the greatest force being acted on it. So what is the largest artery we have, right? So in terms of the diameter of the blood vessel, well, what is the aorta is going to be the largest, right? Nothing's going to be bigger than the ascending and descending aorta. the abdominal aorta. Well, that will also be, the aorta, also be receiving blood directly from your left ventricle. So it's going to feel also the highest pressure as well, because it's receiving blood right from the left ventricle. So what happens? The abdominal aorta is usually the one that feels the greatest amount of force. And because of that, right, and I say abdominal aorta, any part of the aorta will feel a huge amount of force because of both, all right, of these conditions. High diameter, high blood pressure. This is also the reason why people are prone to what we call triple A's. Triple A's are called the abdominal aortic aneurysm, right? Now, an aneurysm is not the same as a blood clot. An aneurysm is when the artery, because of pressure, because of force on it, has been spread out, right? And because it's been kind of spread out, now the vessel starts to thin out. Think about what happens when you have a balloon, that you start adding more and more air from the inside, right? Eventually there's so much air, it's gonna burst. That's what's happening here, right? And when triple A's receives a lot of pressure like this, it can burst, right? We call it, it can dissect. A dissecting aortic aneurysm actually killed one of my friends that work here, right? And we only got to meet him a few months, and he only worked here for about 1.5 years. So we, went and had a couple of years together as a group, right? But he died because he had a triple A that dissected in class, right? The only good news, and this sounds terrible, right? And it's not good news. None of it's good news. But it wasn't at METC. That's terrible to say. The only good news, right? Out of all the bad news, that's the only one, right? He happened in class. They tried to do CPR, and he never woke up, right? He was pronounced dead right when he got there. Because when you have a dissection in the aorta, all right, by the way, a dissection in the aorta is also what killed John Ritter, right? The, what is it? Three's Company, I know you guys are too young to remember that, but Clifford, the big red dog, right? The voice of him, right? What is it? He also had like a family show on at the time, and it was like devastating to people. He died literally on the spot right there. And even if he was in the ER, there's very little they could have done. Because when your aorta dissects like that, all that blood just pumps outwards into your thoracic cavity. And no blood is going to be pumped to the brain, right? He immediately passed out, and he passed out so quickly that he didn't even feel anything. Now, all is because the larger the vessel, and you add to it or multiply to it the pressure in those vessels, the more likely those vessels are to rupture. And again, an aneurysm is a thinning of the actual artery. As it thins out, it's more likely to leak. Right? So you guys have probably heard of, friends that have, or I have a lot of friends that have gone through this, but I had a friend that used to party a little too hard. And he, at like age of 24, had an aneurysm rupture in his brain. And somehow he survived it. Usually when you have a rupture and an aneurysm in the brain, you don't survive those. But he survived it because he was so young, and even now he's alive, he still parties too damn hard. But still, right? I know, right? You think you learn. Now he's 50 and parties too hard. But that is the reason why these arteries are more prone to have kind of thinning or aneurysms. All right, we'll stop right here.